In this lesson, we're going to take the ideas from similar triangles and try to extend them to situations that involve just one triangle. We can do this because we know the idea of proportions. If I have an angle in a triangle, and that angle doesn't change, well then the proportion between the sides won't change either. The triangle might get bigger, it might be twice as big, 3 times as big, 4 times as big, but the proportions between the sides will always stay the same. So we're going to look at a special instance of this. We're going to look at triangles that involve right angles, okay, 9 degrees. These kinds of triangles have relationships between their sides. The sides have names. We're going to start labeling them. Okay. So one of these labels we already know. You already know the hypotenuse. The hypotenuse is the side across from the right angle. But the other two sides also have names, and we name them in relation to a given angle. So this symbol down here, we call this theta. Theta is a given angle. Now sometimes I know the number, maybe it's 30 degrees. Sometimes it's my x, my unknown. I want to figure out the angle, but it's an angle. The other two sides can be labeled according to where that angle is. The side across from that angle is called our opposite. The side beside it is called our adjacent. Adjacent is just a fancy word for a side, beside. Okay, so the easiest one to find is the hypotenuse, because you know for sure it's across the right angle. But if I move the angle, the names can change. So let's take a look at some examples here. So I want to label these triangles according to the given sides. So the first thing I'm going to look at is, can I find the hypotenuse? From the first triangle here, the hypotenuse must be across from the right angle. It's got to be up here. I then label my other sides according to where the given angle is. So here's the given angle, theta. Across from it, in other words, opposite to it, is right there. And beside, adjacent, has to go right here. Okay, but if I move the angle around, I can do the same thing. Let's look at the next example. Across from the angle is the opposite side. So it's across from. Adjacent is beside the angle. Now some people might say, well, isn't this beside the angle right here? But it can't be, because that has to be the hypotenuse. Hypotenuse must be across from the right angle. So the adjacent has to be here. So that's what it's saying. If you do the hypotenuse first, it lessens the confusion about which is the adjacent side. Opposite is pretty easy to find. It's across from the angle. Adjacent can be a little more confusing. Okay. Once we've labeled the sides, we can then start setting up some problems. Okay. These problems take the ideas of similar triangles, and then we extend them. So if we take a look at this set of triangles here, these are two similar triangles. I know they're similar because they have the same angles. They have a 90 and a 30, a 90 and a 30, which means this has to be a 60, which means I can figure out any of the other sides in these two triangles by using similar triangles. I could say if I wanted to, x and y and z, that 6 has to match with y, 8 has to match with x, and z has to match with 25. And this would be totally fine. I could do this. But an even more important idea for us is, what if I had another triangle? And I knew this triangle had a 90 and a 30 in it. Well, I know that every side in this triangle has to be proportional to both of these other two triangles. So if I could figure out the scale factor between any two sides, let's say I knew this was 50, in other words, it's double this one, well then I would know it has to be double that one. So the idea here is, if I know an angle, one angle, 30 for instance, and I know one other side, in this case 50, I can figure out this entire triangle based on the proportions between the sides, the scale factor between them. Okay. As I was saying earlier, there are 3 sides, so there are 3 different kinds of proportions we can figure out. And we call these the primary trig ratios, or trigonometry ratios. Ratio number 1 is called the sine ratio. And the way it works is the sine of your angle. Remember, this is the angle. It takes the two sides, opposite and hypotenuse, And the ratio between those forms a scale factor. So if I know an angle, I can figure out either of the two sides. We have the cos ratio. It's adjacent over hypotenuse, and tan is opposite over adjacent. So notice there's different combinations of sides here. And the order is important. It has to be opposite over hypotenuse. If it is that, then you know it's the sine ratio. To help us remember this, we use a word called SOHCAHTOA. SOHCAHTOA. And where that word comes from is the first letter of each of the words. The sine ratio is the opposite over the hypotenuse. The cos ratio is the adjacent over the hypotenuse. And the tan ratio is the opposite over the adjacent. SOHCAHTOA will allow us to solve problems. So let's take a look at an example. And there's a lot of big ideas here. So we're going to take a look at some examples. So example 1. Write down the ratio for the tan x, sine x, and cos x. Now putting the letter x here is saying, here's my angle. Angle x. Based on angle x, which is right here, I can label my triangle, the three sides. This side would be my opposite. This side is my hypotenuse across the right angle, which means this is the adjacent. And based on SOHCAHTOA, I can now write down the three ratios. The sine of my angle, which was angle x, equals opposite over hypotenuse. The opposite value is 15. The hypotenuse is 25. The cos of x. Cos is adjacent over hypotenuse. So 20 over 25. And tan is opposite over adjacent. So 15 over 20. And there's my three ratios. And I'm going to teach you down the road how we can actually solve this to figure out what the angle is based on the scale factors we have. If we do part B, how would the ratios for angle y be different? Well, if I were to do angle y, I need to use this as my labeling thing, which makes this side the opposite now. This is still the hypotenuse. That hasn't changed. It's across the right angle. But now this one down here becomes the adjacent. So that's going to change some things. When I do sine y, the opposite is now 20. Hypotenuse is 25. When I do cos of y, the adjacent is now the 15 over 25. And when I do the tan of y, the opposite over adjacent becomes 20 over 15. So you'll notice if you compare the two ratios, sine became a cos, cos became a sine, and these two things kind of flipped over from each other. So you have to be very careful which angle you're using when you do your labels. It'll totally change the problem because it totally changes the fractions, the ratios. Okay, so that example, just about learning how to set things up and put them in the right spots. The next example about using your calculator. So there are different kinds of calculators, and if your calculator doesn't work in the way I explained it right now, you're probably going to have to come in and see me to figure out how to do the rest of this, because you probably have a backwards calculator. Okay. Once I have a ratio, sine's a ratio. It's the opposite of the hypotenuse. Okay. And it's based on an angle. I can figure out the scale factor for those two sides based on the angle that I have. And I can do that by using my calculator. My calculator is programmed with every single possible scale factor for any single angle. So, take your calculator out, make sure it's on degrees. It should have a little DEG, or does the D at the front, at the top, okay, and type in sine 36. It should come out to 0.588. And what that means is, if you had a right triangle that had a 36 in it, the opposite side, whatever this is, opposite, and the hypotenuse, the ratio between them, the scale factor, is 0.588. Every triangle, no matter how big it is, the ratio between this side and this side with a 36 always comes out to 0.588. So if I know one of the two numbers, I could just figure out the other number. And if we try the next one, the tan of 78. Type into your calculator. You should get 4.70. And the cos of 12 should come out to 0.978. And just making sure we can find those buttons on our calculator. Okay. If I have the ratio and I want to work backwards to figure out the angle, we can also do that. So forwards and backwards here. So in the second example, this one down here, I know that the cos of some angle comes out to 0.866. In other words, the ratio is given, find the angle. We can do this by taking what we call an inverse. And I'm going to take the inverse of 0.866. So whenever I want to find an angle, I'm using an inverse. On your calculator, the inverse is a second function. If you find the word cos in little small letters right above it, it should say cos -1. That's an inverse function. So if you type this into your calculator, you should end up with basically 30.0 degrees. Okay. So for any triangle that involves a 30, the ratio between the adjacent and the hypotenuse, the cos ratio in other words, always comes out to 0.866. And we try the second one. I want to do an inverse sine this time of whatever 0.2345 comes out to. And using your calculator, you hopefully get 13.6 degrees. Okay. So now we know how to set a triangle up. We can label it, sine, adjacent, hypotenuse, opposite. We know how to put the right things in the right spots using SOHCAHTOA. We know how to use our calculator to actually calculate either ratios or angles. So I can put it all together. And we're going to put it all together and take a look at the 3 questions we can do with SOHCAHTOA. There are only 3 questions. Okay? The words sine, cos, and tan, the ratios are interchangeable, but there's only 3 places we can put the x. So let's take a look at the first problem. Whenever we come across a SOHCAHTOA question, we know it's SOHCAHTOA because it's a right angled triangle, we label our sides. So the first side I got is a hypotenuse. The second sides, or the other sides, depend on the angle. Here's my angle, so this is my opposite. I'm only going to label 2 sides, the 2 sides that I care about. I care about the hypotenuse because it has a number. I care about the opposite because it has an x. I don't care about the adjacent because there's nothing down there. The reason I do that is I want to look for the word SOHCAHTOA. Think of this as 3 separate ratios. What has an O and an H in it? I see an O and an H right there. That tells me I'm using the sine ratio. So the sine of the angle I used for labeling, that was 72, equals, it says OH, so I put the O, the x value, over the h value, OH. Okay, there's my setup. I want to solve this now. To solve it, we're going to cross multiply. So imagine I bring a little 1 underneath here. 1 times x makes x. 36 times sine 72 is 36 times sine 72. So what I'm doing is I'm taking the idea of here's my ratio, okay, the scale factor, if you will, and this triangle has a side of 36. I need to figure out in the corresponding other triangle, what does it come out to? If I type this into my calculator all at one time, I should get 34.2. So that's how big the opposite side is. That's it. We're done. That's problem number 1. Problem number 2, we're going to do the same 3 things. We're going to label the sides we care about. Step 1, my hypotenuse. Here's my given angle. Beside it is my adjacent. Step 2, we're going to figure out what uses A and H, which looks like a cos thing, and we're going to fill the right things in the right spots. So the cos of my angle equals my A, adjacent, over hypotenuse. A and H. I know it goes in that order because that's what cos says up here at the top. And then we're going to cross multiply. Okay, a little imaginary 1. 1 times 48 is 48. X times cos 40 is x cos 40. Unfortunately, this time, I don't have x by itself. In the first example, I did. I had x just right there. It was easy. But this time, I don't. So to get x by itself, I have to think of this as, well, those are multiplying. So to separate them, I need to bring the cos 40 to the left and divide it. Okay, so this is problem 2. When the x was on the bottom of the fraction, it's an extra step. You cross multiply, then divide, and x should come out to 62.7. Okay, so we prefer the ones with the x on the top. Those are really quick. They're just 2 lines. If x is on the bottom, like this one, well, it's 3 lines. We've got to do 3 parts and pieces in between. Okay, and then the last type of question. So x on the top, x on the bottom, or in the third case, x is our angle. The process stays the same. Label, hypotenuse. And beside the angle, it's the adjacent. A and H. If I think about saw, ka, toa, A and H is cos again. Okay, so the cos of the angle adjacent over hypotenuse. So this is our third problem. X is the angle. To find unknown angles, I use inverses. So I'm going to take the inverse of 12 divided by 24. Oops, 24. And I'm going to type it in just the way it looks, brackets and everything. So 12 divided by 24, take the inverse of that. Now I know 12 divided by 24 is a nice number, it's 0.5. But when it gets to be a messy number, I don't want to round things off. That's why I like to use this dividing in brackets. If you do this right, you should get 60. Okay? So those are our 3 examples. That's how this is going to work. I've got 2 left for you to try. So pause it, see if you can try the next 2. So let's try D. Label, opposite, adjacent, beside. That tells me it's a tan question. Opposite over adjacent. I'm going to cross multiply. And then I'm going to put it into my calculator. And I get 7.21. And last one. I'm going to label. It's cos of the angle is my adjacent over hypotenuse. I'm going to take an inverse of what 11 divided by 19 comes out to. This is one of those messy ones I don't want to round off. And I get 54.6. And there's our introduction to trigonometric ratios, or as I like to call it, SOHCAHTOA. Okay, this is the first day of this stuff, so there's lots of little ideas here. If you're stuck with some things, come see me. There's some quick questions to try it, and it looks like a lot, but they really are going fast. Some of them are just labeling, some are just using your calculator. The second page is where you're actually trying to solve things. If you're stuck, as I said, come see me, because we're going to keep building on this the next couple of days.